Greetings, and welcome once again to my new calculus channel. My name is John Gabriel. So, in the previous videos, these Why Your Mainstream Calculus is a Load of Bullshit 6-part series, we talked a lot about epsilonics, etc., etc. But guess what? The nice thing is that limit theory is not required in calculus at all. Okay. And the proof of that comes in something called my geometric or my historic geometric theory, which is this formula that you see here. Okay, so let me explain everything that is on here to you. So um, let's start at the beginning. Newton, Leibniz, and others were trying to figure out how to calculate the slope of this green line. Okay, that's what they were trying to do. They were trying to figure out a method of doing it. And it was a very difficult problem for them because they were not geniuses. And I mean, it takes a genius like me to find solutions to problems of this nature. Okay. Um, it takes somebody who's incredibly smart, not just a common, ordinary Joe like Newton or Leibniz or Cauchy or any other one of those idiots. So, what did Newton do? Well, he decided he was going to approximate this tangent line slope using the non-parallel secant line. Okay, this non-parallel secant line. That's what he did. So he figured that as long as he could just keep on bringing those 2 points closer together, then the slope would start becoming closer to the slope of the tangent line. But of course, Newton was a master of approximations. He used divide and conquer approaches. And this method of Newton's and Leibniz's is a brute force approach. Okay, it's completely brute force. It's not a valid systematic solution, and it's not a solution at all, as you'll see shortly. Now, what is dy dx? Let's just get rid of it. Dy dx is a symbolic fraction, and dy and dx are symbolic differentials. Okay, that means it doesn't matter where you put them along the tangent line. The ratio or the fraction of the symbolic differentials is a derivative. Okay. And so, yep, doesn't make any changes to where you move this point. This slope here is always the same. Now, in the new calculus, you don't have that problem because in the new calculus, you use a parallel secant line, which always has the same slope as the derivative. I mean, as the tangent line. Okay, always has the same slope as the tangent line. Now, you might say, but what happens when that point goes there? Well, it shouldn't go there. If it does go there, you've made a mistake. In other words, you haven't understood what's going on if you do that. Why? Simply because if you get there, then you don't have a secant line anymore. Okay? You don't have a parallel secant line, nor a non-parallel secant line, nor any secant line at all. Okay? So it's just a stupid question if you ask that. Then what is the Holy Grail? The Holy Grail shows you that. So what have I done here? I've taken this same non-parallel secant line and I've positioned it right here on the x-axis. I've done the same with the tangent line. And the reason I've done that is so that I can see what happens as these 2 points come together. Okay? So now the Holy Grail, which is this identity here, by the way, has nothing to do with the fundamental excrement lemma, which you'll find on Wikipedia. This is just nonsense. This here is talking about a bullshit concept called an infinitesimal. Okay, and there's no such thing. So X that. Don't even go there. It's a load of rubbish. Now, if you want to learn more about my historic geometric theorem, you'll come to this article here and you'll study it. It's not going to be doable in just a few hours. You're going to have to think about it. There's a lot to this, okay? So as you can see, the identity doesn't have anything about limits in it. Okay, there's no garbage about limits. That's just drivel that's been uh, formulated by my intellectual inferiors of the past 400 years. maybe longer than that, probably 2,000 years. So you don't need to use limits. And let me explain why. Okay, so what's going on in these diagrams? So this is the point of tangency. This is the tangent line. I've taken that tangent line. It's this line here. Okay. Okay, that's this tangent line here. I've taken this secant line. It's this line here. And I can do that. And anything I do to this side here will happen to this representation here. This representation on the left here, this non-parallel secant line, this tangent line, and the slope difference are what form the Holy Grail identity. So what's happening here? What is this Q of XH? Well, this Q of XH is really what fucks you in your face and your rear end and your professors and all the morons of mainstream mathematics academia of the last 400 or 500 years. Okay, it tells you you're stupid. I mean, it can't help but tell you you're stupid because all mainstream mathematics academics think that this here is an error term, but it's not. It's the slope difference, okay? It's the slope difference between the tangent line and the parallel secant line. So obviously that slope difference is going to get smaller as these 2 points approach, but it doesn't really get smaller for different secant lines, okay? All these secant lines have a fixed slope and a fixed difference with this tangent line. So for example, if I have that secant line, this 1.45151 is a constant slope difference. It doesn't change for this secant line. It doesn't change for any secant line. If I move down here, this is a different secant line. So it has a different slope difference. Okay? But it doesn't change, right? It doesn't change because each one of these non-parallel secant lines are different. So what you have here is an equation of slope differences, not slope differences, of slopes. The left-hand side here, this red fx plus h minus fx, is just the slope of this non-parallel secant line. F prime of x, we didn't have to call that. We could have just called it maybe TS for tangent line slope, is this the slope of this tangent line, and Q of xh just a difference. And you can see what's happening here, right? So it's important to bear in mind that the slope difference in terms of rise over run is applicable to the Holy Grail. You cannot take it in terms of angles, okay? Because Newton was not working in terms of angles. He was working in terms in other words, slope in terms of angle. He was working in terms of slope as rise over run, okay? Remember I showed you that earlier on, or have you forgotten already? See, rise, this 5.255, over run, okay? And of course, it was always wrong because even when you get there, what happens? You don't have anything, right? You don't have a non-parallel secant line slope, you don't have a tangent line slope, and you do not have a slope difference, okay? Now, the driveling, sniveling morons known as your mathematics professors and teachers will maybe write something like this. They might say lim of that as h approaches 0 is equal to f of x plus lim as h approaches 0 of q of x h. Now you might say, well, why is that problematic? Because this here has a limit of 0, right? Well, it's problematic. Let me tell you why. Because what you're saying is that this tangent line slope somehow becomes equal to this limit, but there is no rise, over run that ever represents the tangent line slope. In other words, it doesn't matter doesn't matter how many of these rise over runs this f of x plus h minus f of x over h. It doesn't matter how many you get. And you see this number here, this is the difference. This is the expression of that rise over run. Doesn't matter how many you get. There is none that represents the historic geometric, that doesn't represent, that fulfills, or uh, what is the word for it? That no, my mind has gone blank. There is no rise over run at that point. That's really what it boils down to. Okay, so when you get to that point there, I mean, this is just an imaginary thing. It's not real anymore. So ultimately, what happens is this: we don't even need to care about this term. We don't need to care about the q of xh term because it's a slope difference. Okay, it's a slope difference. We could just ignore it. This is what we want. Now there is a time when this here is exactly zero, and the only time it's zero is when f is a linear function, in which case f of x plus h minus f of x over h is equal to that, okay? Because that is the slope of a straight line, right? That's the only time that this here is equal to zero. In every other case, it's a slope difference. It's not an error term, it's a slope difference. And yes, we can ignore it. And why can we ignore it? We can ignore it because we have the derivative, which is f prime of x. And how do we know that we have that? Well, very easy. You study this article and it tells you. It tells you how to find both the derivative and the slope difference. And it gives you a proof of the theorem. Okay, this isn't stuff that I just dreamt up of one day and said, wow, this is how it works. No, I've been thinking about these things before you were born. I'm actually 63 years old. I mean, most of you little morons who've got PhDs right now weren't even spewed out by your father when I was thinking about these things. Okay. In fact, your father probably hadn't been married yet or whatever. That's besides the point. Okay. So, you little dimwits need to understand that when I talk to you about these things, I know what I'm talking about. There's nothing wrong with me mentally. The problem is with your math professors and your teachers. And of course, you, because you've been taught the wrong way. And so your mind has become syphilitic, just like theirs. In other words, you're incapable of thinking properly. That's a problem, you know. Now, I feel sorry for you. And this is the reason why I'm going over this, because you're incredibly stupid and incredibly misguided. And yes, I mean, I've given you videos on this before, but I probably haven't spent that much time on it. But if you have any questions on this video, post them in the comment section. If I detect an attitude, I won't even read your comment. You'll just get blown away. Do you understand that? Now you might say, why is this important? Well, it's very important because from this Holy Grail, you also get the definite integral, right? There's a lot to this, folks. There's a lot to this. So from the Holy Grail, the definite integral is simply f of x plus h minus f of x, and it's equal to h times the mean value of all the ordinates of f prime in the interval x to x plus h. Okay, so this here is the definite integral. It's beautiful stuff. It's amazing. It's all geometric. It's got nothing to do with your bullshit theory of limits, with the toxic crap of set theory or Zermelo-Fraenkel axioms or real analysis BS or topology or any of that drivel. It's got nothing to do with that. It's all geometric. That's how it was intended to be. And here's another thing I want to talk about just one more time. Okay, let's talk about this. The mean value theorem. Okay, Now this is the mean value theorem, which says f prime of c is equal to f of minus f of x over h. Okay, that's what the mean value theorem says. It's unremarkable that if you have a curve like that, x and x plus h, it's unremarkable that there is a tangent line there that is parallel to that secant line. Totally unremarkable. Guess what? Euclid and the ancient Greeks knew this over 2,300 years ago. You can construct a line that is parallel to this tangent line anywhere on the curve. You could just put a point there and construct a parallel secant line. Okay? No problem. And it was proved in the elements. I mean, that masterpiece, which most of you morons think you know, but you've never understood. Okay, so it's vitally important that you study the elements, because from the elements you get everything. You get geometry, you get mathematics, you get architecture, science, anything that you can think of in STEM or physical sciences or anywhere else. All that is dependent on the foundations, which are the elements, not the bullshit of set theory. Okay, so the mean value theorem. Okay, so this is the mean value theorem. So what I want to tell you here now is this, that this is the reason calculus works. Okay, it says, what does it say? It says that there is a C somewhere inside here, a C, point C, such that this length here, I wanted to change the color. This length is the arithmetic mean of all these y ordinates. Okay, of all the y ordinates, not of f, but of f prime. Okay, so f prime may not be like that. So this isn't, realistically speaking, a good diagram. I would have to put f prime on here, and then one f prime would probably be a straight line. So it would probably be something like that, and then it would be all those y ordinates, and this would be, the dark red line would be the arithmetic mean. And so if you've got the arithmetic mean, if you have a situation like this where you've got one line in here, which is the arithmetic mean, then you can find the area of this figure. It's just that line multiplied by the interval width. And that's how calculus works, by the way. When you have a curve like that and you find the area, you're using the mean value theorem. Okay, you're using the mean value theorem to find that curve. It's true also when you have a curved surface like this. But in this case here, you're not dealing any longer with just a straightforward product of arithmetic means, but you're dealing with, in your mainstream calculus, you're dealing with vectors, which are called normals, and then you're taking the arithmetic mean of those little rectangles. And that also turns out to be possible because of the mean value theorem. Okay, so you cannot do anything in calculus. So for example, if you have f prime of x dx from x to x plus h, like that, you cannot say it's equal to f of x plus h minus f of x unless both these functions are smooth. Okay, they have to be smooth. What that means is, if you know what this is, like 3x squared, you can't just say this is x cubed unless you know that x cubed is smooth. Both f and f prime have to be smooth. You need to understand that. Okay. So Wikipedia, the entry on Wikipedia about the fundamental theorem, they have no clue what it is. And it's not just continuity that is required. You need smoothness. Okay, so without smoothness, methods of calculus are a bunch of garbage. You can't use them. Okay, you can't have a curve like that which isn't smooth and then use this fundamental theorem or the mean value on this. Because think about it. Let's just clear this out. Think about it. Look. So If you had a curve like this, whoops, like that, okay, and you had the boundaries like that, and you choose a point, let's say, with a tangent line there, like that. Where is the line, the tangent line that is going to be parallel to that between these 2 points, this point and this point? Where is it? Can you see what I'm saying? Okay, you need to think, and you need to think a lot because your brains have been polluted by mainstream garbage. So you're unable to think clearly. It's a problem. It's a very big problem. Okay. So, anyway, that is what I wanted to share with you. And going back to my demonstration here, I can place a link to this applet, which you can download and play with. It'll help you understand these things better. I'm John Garville, and this is New Calculus Channel. Till next time, goodbye.